It should be on. Good evening, everyone. This is Astronomy 10, Evergreen Valley College online course. And today, in fact, I'm showing here on Canvas webpage where you should go to find all these videos of these chat rooms. I always upload, and so I wouldn't say that you all should watch it again. That is a testimony of endurance, but is there, especially if we go over some of the subjects you are having hard time to go through, and also the book links comes right after, and is all divided by the week in which we are pretty much focusing on the topics of the week we are pretty much covering. And this week, April 2nd, we are pretty much going over chapter 15. We are studying the sun. So basically, in our course, what we do, we have a couple of months or less in which we focus on the sky and the history of astronomy and what are the tools that astronomers use in order to come up with ideas and knowledge about the universe. So pretty much it's light. Um, the main point here is that we, as of now, we don't have a technology to go out and explore other galaxies, right? Or other stars. Um, we don't have the technology to visit all the galaxy clusters, rich and poor, that populated the universe. So how do we know that all these entities exist? How do we know that all these groups exist? So how do we know all of that? Because of light, and because we know how to collect lights with the telescopes and detectors, and we know how to interpret the interaction between light and matter. We understand spectroscopy and photometry as the basic tools astronomers use in order to build up knowledge about the universe. So today we are kind of moving out of this basic astronomy, historical astronomy, and the sky objects, moon and the planets, and we are using the sun as a trampoline to explore other stars, in fact, other star systems. And more than that, we are using the sun uh, to initiate the study of stellar evolution. So we know the sun came from gas. We studied that before. But we don't know what's going to happen with the sun, what's going to be the future of our solar system. Um, and we know we are made of atoms. We know that the basic atoms, the basic building blocks of our bodies, of our environment, are astrophysical entities. So they were produced not here on Earth, but they were produced outside by stellar processes or by cosmological process like hydrogen and helium. Um, and so we are kind of entering now a different realm, the realm of stars, and what's the purpose of stars in the big universe, basically. Um, so the subject of this week is the sun. It's the first star we are studying, is the closest one, is the one we know the most, and also is the one that has the most observations. And in fact, astronomers use these observations to calibrate and to fine-tune models for other type of stars, of other surface temperature, and so on, so on, so on. So what is important about the sun is to know what is the interior part of the sun, the three main regions the sun is made of, and the three external regions the sun is made of. So that's it. The interior part, the exterior part, and what each part contributed to what we call the sun. So basically that's what it is. So let me pull up some slides. This is a picture with a mask that is blocking the sun. So we are not seeing the sun. In fact, there is a sun here in the middle, but the sun in the middle is being is a picture that is superposed to another picture. They are not taken together. So basically, the dark disk is a mask that is blocking the sun, and by doing so, we see what is outside the sun. So the last luminous gas that surrounds the sun, in fact, is corona. All you were talking about corona before we start, so that's the solar corona is right there. Is one of the regions, the external regions in the sun. If we go, there are satellites out there, and we can, in fact, visit. Let me see if I can find it. There you go. SOHO is one of the satellites, and there are cool movies. Let's say this movie over here. See if I can show in my computer. There you go. So it's the same idea. You have a mask that is blocking the sun, and see this little thing over here? That's a coronal mass ejection.
Comet.
This beautiful comet coming by, and another coronal mass ejection. So those are energetic type of events the sun goes through, and we can see them in all its perspective if the sun, the bright disk of the sun is blocked as it has been blocked here. So I can bring more of it. Oh, 31 megabytes. That's gonna take quite a while to download. So let's take a smaller version. Oh, that's another comet. I don't wanna see that. How about this one? More coronal mass ejection. That's a short one. Other movies show a different part of the sun. Try this one. And there is a spot. So, in fact, can I take this out? There you go. That's a sunspot going across the sun. Looks like, but looks like also a migrating something.
Mercury.
It's a Mercury transiting, right? So it's not a sunspot. What I'm talking about? That's Mercury transiting. Too perfect.
Wow, it's real high or low.
I guess it depends on the time it takes to do that.
Yeah, well, we have the time ticking up there. And Rick, we could use the same mathematics we use with your video,
Yeah.
and confirm if everything is nicely done. You know, we know Mercury, we know the distance, we know the time of its orbital period, everything. Let me see what is 4 planets. Oh, this would be nice. We see the sun and we see the planets passing by.
We're supposed to be seeing something?
Not yet. It's charging.
Okay.
Yeah. 4 seconds. 3.
There you go. That's a planet, saturated, and the sun with its coronal mass ejection that looks like smoking a cigar. And some of these planets in respect to the sun is prograding, another planet retrograding. So with respect to the sun, you can see these planets orbiting quite well, and you have a star cluster passing by up here. Looks like Pleiades, huh? It does look like
almost.
Pleiades. Yeah.
What day was that?
Well, 2000, April 2000. This is an old video.
I don't see the. Hard for me to see the time. Is this you're talking days when this goes by, or months?
There is the time is 2000 May 2000 on the 14th, 15th.
But the time period is this whole time lapse thing. Is this over a day, a week, a month?
Oh, this is 1 day. 1 day.
A month.
Oh, a month. Yeah. That's a month. Sorry.
Oh, I see it now. Okay, down at the bottom.
Down here.
Okay.
Yeah.
Yeah, it looked like it started in March.
That's correct. Yeah. Now, May 12, 13, 14, 15. There you go. And the planets are there. So
It looks like the Pleiades.
It looks like Pleiades, right? So it shows all this energetic going on. The sun is a very stable and quiet star, but when you look in details, there is lots of activity going on, and this activity is primarily driven by its magnetism. So let's pull up more of the figures. And here's another example of the sun's magnetism. It's called prominence. So this arch is pretty much magnetic field lines that comes out of the sun. It's anchored in the solar subsurface region, and we can see it, especially if you have the chance of going to the observatory during daytime. If I or Rick is there, we can put a filter that allow us to see these loops, this arch across the solar limb. We don't see it in the nice way as it is here, but we can see the entire solar limb, and then we can look for these arcs looping around. And here Earth is showing for comparison. We have a little Earth there. See how these arcs are exceedingly large. Now you can also look down on the sun. You have these dots, these granulations going on there. These granulations are the result of convective motions, and convection is a process by which hot material moves from hot regions to cooler regions and transfer the heat to this cooler region. So you can see convection in the oceanic current. You can see convection in the atmosphere when this floor, the rocky floor, is too hot, and then this hot air, which is warmed up by the floor itself, expands and moves up and cools down in the upper atmosphere, and when it cools down, it falls back. So the circulation exists in the sun as well. You have the sun with the hot central part and a cooler surface, and then you have this circulation going on called convective motion. And the last layer of these convective motions appears in the atmosphere as this so-called solar granulation. Each granule is about 3,000 to 5,000 kilometers, just to have an idea. So Earth radius is about 6,000 kilometers. So we are pretty much seeing some structure that can be compared to our own planet. So this is Cecilia Payne, who did major work and helped us to better understand spectroscopy and stellar evolution. And we use most of her work that she and so many other women did in the beginning of 20th century to help to establish a ruler by which we can establish and measure distances in our galaxy and then in the universe. But let's take a look at the solar interior. So the solar interior, in fact, here you can see the sun at all. So we have a slice of the sun. The interior part, the central part, is also the densest one, but it's gas. It's not liquid or solid. The sun and all the stars throughout is a big uh, ionized gas we call plasma, and the plasma in the very core is the densest one and also is the hottest one, and the conditions are such that hydrogen atoms, which is the most populated atoms in the universe, 75% of it is hydrogen. 75% of the material made of protons, neutrons, and electrons. There are other stuff there. We don't know what it is, called dark matter. I have no idea what it is, but it knows there. But the material we see, we can measure, interact with light, is called baryonic matter, made of protons, neutrons, and electrons. 75% of that is hydrogen. So hydrogen is the most abundant atom in the universe, and it was created when the universe itself was formed in the Big Bang process. Um, but the density and the temperature is so high that conditions are such these hydrogen atoms fused and formed the heavier helium atom. But as a result of this fusion reaction, helium is formed, but not only helium, but also energy is produced in the shape of gamma rays, which is the most energetic electromagnetic radiation, and also a particle that interacts very little with matter called neutrino. And neutrino is also created, and once creates, escapes the solar interior. So basically, if you think about the sun, the core is where energy is produced. The solar core or central part, about 25% of the solar radius is pretty much determined the limits of the core. That is the sun's powerhouse, is where energy is being produced. And then here is kind of depicted with this greenish coloration, which indicates high temperature in there. Now, once this energy is produced in gamma rays, so these gamma rays moved outward, and this energy is imparted equally throughout the solar interior in what is here depicted with this orange coloration, and that is called the radiative zone of radiative diffusive shell. It's a shell where this gamma rays diffuses and changes its frequency. In fact, gives out energy to this interior part and warms it up. And by doing so, it creates some balance in the solar size, if you will. So if you think about the sun as a gas, so gravity tries to compress the sun. Gravity tries to bring the sun to a black hole, if you will. But the energy that is being produced in the core, it helps to balance this inward type of force, and the balance of these two forces makes the sun be stable and of an equal size that doesn't change as time goes by. So the sun remains the same size, throughout the ages. I mean, it has expanded slightly since it was formed, but it's not severely expanding or contracting like premium sequence stars, we are going to study them, are, or like pulsating stars do in a very short amount of time. So the sun has a stable size. And because of that, the solar luminosity, the amount of energy the sun is sending out to space, it doesn't change much, which is pretty good for us. We, as living organisms, don't like when the environment change in an abrupt way or in a radical way in a short amount of time. I mean, life takes time to adapt to a changing environment, and that's why when we studied global warming, it was such an issue because I mean the weather, the climate is changing since Earth was formed. Earth went through periods in which the concentration of carbon dioxide in the atmosphere was much larger than it is now. but life was adapted to that. It took millions of years for life to grow and to respond to these stimuli. But if the atmosphere changed in a short time, like 100 years or 200 years, then the living organism will not have enough time to adapt, and some of them will succumb. So the sun having same, radius and volume for a long time is good for life. That's the first thing. The second thing, the sun's production of energy is kind of stable and hasn't changed dramatically throughout the eons, which also is good for life. And the sun as a star is a quiet star. So if you look at the third region in the solar interior, the so-called convective zones, which is here represented by the circulation, um, the circulation breaks down in its top layer by smaller cells that I mentioned previously as granulation. And these granulations appears in the photosphere and partially in the chromosphere. So the solar interior is the core, the radiative diffusive shell or radiative zone, and the convective zone. So those are the regions we don't see it because is sub atmospheric region. What we see is the atmospheric region, which is comprised of three main regions: the photosphere, which is the region that produces photons and light; the chromosphere, which is the region above the photosphere where lots of activity occurs. We can see lots of flares coming up in the chromosphere. And the last of these three atmospheric regions is the corona, which is the largest one, the most extended one. So in the photosphere, you can see this nice phenomena called sunspots. So sunspots, they appear and they appear and they rotate along with the solar rotation, and they can be used even to determine the solar rotation. So how long it takes the sun to complete a whole rotation. And what we find is spots that are seen close to the solar equator, they complete a turn in about 25 days, whereas spots that are formed in upper latitude regions like 35 degrees or 40 degrees above and below the equator, they take longer. They take about 35 days to complete a whole turn. So altogether indicates the sun rotates faster in the equator than it is in high latitude regions. And this differential is called differential rotation. So the sun rotates differentially in the equator from the pole. And because of this differential rotation, the sun has an excess in magnetic activity. So magnetic activity, which we are seeing, the sunspot is one of the results. We saw the prominences, we saw the coronal mass ejection. All this magnetic activity is triggered by these two phenomena. One is the convective motion of the solar interior, which it twists and pretty much that's the proper term to mention. It twists magnetic field lines, but also the differential rotation we observe in the sun. Here's a closer picture of the solar granulation. And in the right-hand side is one of the sunspots visible. In our telescope, if you have the chance of going to the observatory, you might be able to see sunspots, but with the proper filter, with a clear filter, and if the conditions are good, you might see this intermediate region between the dark region called umbra and the granulation itself, and this intermediate region is called penumbra. And astronomers can use spectroscopy to determine surface temperature of these objects or these regions, in fact. And the sunspot has about 4,000 Kelvin, whereas the average surface temperature is about 6,000 Kelvin, and the penumbra goes in between 5,000 Kelvin or so. That is another side view with the photosphere, the chromosphere, and corona. Chromosphere, the name comes from chromium, and when astronomers first saw the chromosphere against the solar limb using filters, pretty much H-alpha filters, they knew it was kind of a reddish in coloration, looks like a chromium, and that's how this name chromosphere came by. And because of spectroscopy, now we know what it is. It's pretty much hydrogen lines that are produced in it. And the hydrogen line that is produced in there is H-alpha, which students can see in the laboratory. And Trisha, you will be able to see it this Wednesday. I put a hydrogen light bulb in there, power tube, and then you might be able to see this H-alpha line pretty clearly in the laboratory. This is a side view. It's a side view of the solar atmospheric temperature. The photosphere, it goes in a sense, the temperature drops down. The chromosphere is sort of stable but rises up, especially where these emissions in calcium, magnesium, and all these details, you don't need to worry about it. And the corona, that is the hottest region. So in average, you could say the photosphere is a region that is about 5,000, 6,000 Kelvin. Chromosphere, you can detect it using features that are sensitive to higher temperature, like 7,000, 8,000 Kelvin. And the corona is a region that you can visualize using features that are sensitive to median Kelvin, which indicates how hot this region is, although it's very light. It's not dense at all. So the photospheric is the densest one, and then the density diminishes as it goes up to the corona. And the corona is the most extensive one. There is another view of the solar photosphere with the granulation, and these spikes you see kind of rooted in the photosphere are called, in fact, spicules, and those are pretty much driven by the sun's magnetism, basically. They extend out of the photosphere into the chromosphere, and they are pretty much hot gas or jets of hot gas coming out of the photosphere, primarily driven by the sun's magnetism. Again, all this weird and random behavior the sun goes through is primarily driven by magnet and the sun's magnetism. This is a region, so-called coronal region, and so if you think of the sun radius as half of the solar diameter, so half of the picture of the solar disk here represents the solar radius, right? So the corona we see here, this halo going around, is what? Is 1/3 or 1/4 of the solar radius. But the corona can be extensive. The suns went through active moments in which corona was 20 times as big as the solar radius, just to give an idea. It was an extensive corona, as a result of the solar activity, basically. But you can see the so-called corona hole, these dark regions in there. It's not a hole itself, but it's because these magnetic field lines in these regions happen to be open to the space, and is dragging gas around out of the sun. The gas evaporation in these coronal holes are more efficient than in other regions. So if you think of magnetic field lines closed this way in most of the solar coronal region, then the gas is trapped. But when the magnetic field lines open up, then the gas escape and goes out. That's where the coronal holes are for. Now, another phenomenon associated with magnetism, but not the sun's magnetism, but Earth magnetism, is the so-called aurora borealis and aurora australis. So coronal holes, as was mentioned in the previous slide, where is it? Right here. The coronal holes are regions in which solar gas, primarily protons and electrons, are escaping more efficiently. But where all these electrons and protons go? Well, they travel through the solar system. But when they meet our planet Earth, they encounter our own magnetism. So Earth has a magnetic configuration, and we studied that before when we studied Earth. And these magnetic field lines, what they do, they diverge most of the solar wind away, so we don't receive this blast at all. But some of these protons and electrons are trapped by the magnetic field lines, and they spiral and they fall onto our high latitude regions. And as these protons and electrons fall, they collide with gas in the atmosphere, primarily nitrogen and oxygen, and the gas pretty much glow. It's like a light bulb, a fluorescent light bulb. They have a gas inside, and you set an electronic current going through the gas, and the gas get excited, and then we see the glow coming in. And the glow is the result of this excitation of these atoms once they get excited by the electronic current. And more sunspots. In sunspots, there is a cycle that is the so-called, there are two things going on with the sunspots. One is the cycle in which the sunspots go. So the cycle is about 11 years. So during 11 years, the number of sunspots one can count in the solar atmosphere grows to a maximum number, and then diminish to almost no spot at all you can count. The last time we checked, Rick was available, and we took the telescopes out, we pointed the sun, we saw nothing, just a clear solar disk. But sometimes the sun has several spots, and there is a technique to count these spots, which is complicated, but then astronomers can count how many spots per year the sun has. And this number goes to a maximum in decay with a period of 11 years. Now, if you use spectroscopy, which is this technique by which you take solar radiation or radiation of any star, and then you create a rainbow, and then with very good detail, you look through this rainbow, finding out features responsible for which are produced by atoms being excited by light or collision. And we are studying this in Astronomy 10L lab now. So you find there are transitions in these spots that can tell what is the magnetic orientation of the sun. And we use a technique called Zeeman effect. So what astronomers found is that the sun goes through magnetic cycle. And these magnetic cycles take 22 years, which is the double of 11 years. So basically, the number of sunspots in the solar atmosphere is pretty much tied to the magnetic cycle. So in 11 years, the sun has a dipolar orientation in which the north magnetic pole, let's say, coincides with this north geographic pole on the sun, and the southern magnetic pole coincides with the southern geographic pole on the sun. And then 11 years later, these reverse. So the sun doesn't go somersault, but the magnetic polarity reverse. And quite strange, Earth goes through similar cycle, except that Earth doesn't take 11 years to complete a magnetic somersault, if you will, but Earth takes 100 million years for that to be completed. So, and the reversal takes few thousand years to occur. So Earth has gone through this period of changes before, and geologists can tell that by analyzing the orientation of Earth's magnetic field that is crystallized and recording rocks. Some more on solar spots. This is Earth is showing there for comparison. And here is a technique called Zeeman effect. That I see this. Oops, in the green. Oops, let me go back. In the green slide, the part B, you have a line that is splitting three parts, right? Kind of a elliptical parts, and this splitting can be modeled and used to determine the sun's magnetism. That's the Zeeman effect. This model is, in fact, is the only model astronomers have so far that explains the sun's magnetism. And this model is the one that indicates the beginning of a cycle where the sun is pretty much dipolar, has a north and a south magnetic pole, and the north magnetic pole is in the beginning of cycle, here depicted, coinciding with the north magnetic pole. So the two coincide. And after a period of rotation, these lines start to be tangled, and eventually it reverses in 11 years. More example of solar activity, the Pleiades, and more example of solar activity. And more in there with solar flare. So even if you go to SOHO, go back there. If we go to SOHO, or did I lose SOHO? There you go. So if you go to SOHO, you have examples of all these magnetism. You have some animations and movies and flares, coronal mass ejection, all of that in there. So just for fun, you can download and put it in your screen as a screensaver, which is a cool one. But basically, that's it. So the solar core is where energy is produced. The radiativity diffusive shell is where energy is transferred to the solar interior and keep the sun stable with a consistent size or volume. And then the convective zone is where energy is moved with mass motion up to the atmosphere. And the atmosphere is a region divided by three layers, if you will: the photosphere, the chromosphere, and corona, with different types of activity. And we can all outline and identify these different regions if we use spectroscopy, for instance, as one of the techniques. Okay. I think that's all I have to say. We are in the next week we are measuring stars, and primarily we are introducing the concepts of magnitude and brightness, which is an important tool when we try to study stars. I mean, we look in the night sky, we look at the stars and we see them with different brightness. So does it mean the brightest stars are closer to us? What's going on? Not necessarily. So stars again come with different surface temperature, different sizes, and so different luminosity. And the size is an important issue determining how bright the star appear to us in the sky and also its luminosity. A bright star might be a very far away star, but is very big, supergiant. And because it's very big, supergiant, it is luminous, and then we can see even being far away. And Cecilia Payne was an astronomer that helped us to establish these rulers, um, enabling astronomers to talk about distances, although we haven't left the solar system yet. All right. I didn't turn on the light in the place I am, and it's all dark here. It looks like a ghost. Just